there's a new way to optimize high-speed designs. JITX generates the geometry from requirements, exports to HFSS, HFSS simulates, and the loop iterates until the structure meets its target. Setup cost per iteration drops to near zero. Here's how it works. It starts with a requirements document. Interfaces, stack up, impedance targets, timing constraints. The AI can use an existing parts library or model complex parts like this FPGA from datasheets. It reads the requirements and then writes all of the design code. Here, an off-the-shelf AI tool reads the requirements and supporting data and writes Python, calling the JEDEC library in phases. Here's the code the AI wrote. Substrate, components, circuits. Running this in JEDEC produces a schematic, applies the constraints, and generates the board layout. RF outputs on fence to coplanar coupled waveguide. These traces are dynamically skew matched. Differential pairs dynamically de-skewed and impedance controlled on an inner strip line layer. DDR5 memory interface. Pin assignment optimizes during routing, swapping byte lanes and bit ordering to shorten routes. That's the design. Now here's the optimization loop in detail. JEDEC generates a 3D structure, a via transition, routing assignment, any parameterized geometry. It exports a full ready-to-run simulation to HFSS, automating the cleanup and setup steps. HFSS simulates and returns S parameters. JEDEC reads those results, adjusts the design parameters, and generates the next variant. The cycle repeats until every iteration is a real electromagnetic simulation on real, manufacturable geometry. Here's that loop running on a scripted via transition. Each frame is a different variant. Antipad shape changes, ground vias reposition, clearances adjust. The S parameters improve with each iteration. The same approach applies to other structures, coplanar coupled waveguide curvature, trace geometry, anything that can be parameterized in JEDEC, which is everything. The optimization loop also works at the full design level. 2 changes to the DDR5 interface. Add ground via fencing to the clock pair at 0.5 millimeter pitch, and tighten the skew constraint on the data bus. Rebuild. The data lane's readjusted to meet the tighter skew. The clock pair now has ground vias along its entire route. What you just saw was requirements to code, code to design, design to simulation, all connected in one loop.